All right, let's get right into it. AI is everywhere now, right? It's on our phones, in our search bars, helping us at work. But behind that super clean, simple chat window, there is a massive, totally invisible world of machinery humming away. So today, we're going to pull back that curtain and see what it really costs to get an answer from an AI.
I mean, think about it. We ask AI stuff all the time, from, simple little facts to really complex questions. But have you ever actually stopped to wonder what the real cost of asking is? And I'm not talking about the few bucks for your subscription. I mean the actual physical resources it takes to get you that answer in a split second.
Okay, so let's start with something we can wrap our heads around: electricity. A simple Google search, something we do without even thinking, uses about 0.3 watt-hours of energy. Now look at a short question you might ask GPT-4o. That number jumps to 0.42 watt-hours. That's a 40% increase in energy for just one simple question. Right off the bat, that's a pretty surprising difference.
But here's the thing. That 40% jump in electricity, that's the cost we can kind of imagine. It makes sense. But what if I told you that's just a very, very visible tip of a much bigger, almost entirely hidden iceberg of consumption?
Because the real story here, the one we're really digging into today, isn't just about electricity. It's about water. You see, AI has this hidden secret. These powerful models are unbelievably thirsty, gulping down millions of liters of fresh water in ways you'd never, ever see.
So how on earth do you even measure this thirst? Well, there's a specific metric for it, and it's called water usage effectiveness, or WUE for short. The idea is actually pretty straightforward. For every single kilowatt hour of energy the servers in a data center burn through, the WUE tells us exactly how many liters of water it took to make that happen. This one number is the key to unlocking AI's entire hidden water footprint.
But this water cost isn't just one big number. It's broken into two parts, what they call scopes. On one side, you've got Scope 1. This is the water used right at the data center, mostly to cool down those thousands of servers so they don't, melt. Almost all of this fresh water just evaporates into the air. Gone. Then you have Scope 2. And this is the invisible giant. This is all the water consumed by power plants, maybe hundreds of miles away, just to generate the electricity that the data center needs in the first place. And this is often the biggest piece of the whole puzzle. So let's put a real number on that on-site Scope 1 water. Just to train one model, GPT-3, researchers figure it consumed a mind-boggling 700,000 liters of clean, fresh water. That's water that literally vanished into the atmosphere just to cool the computers during that single training period.
All right, so you're probably thinking, okay, I get it. AI uses a ton of resources. But, and this is a huge but, the story gets way, way more complicated. The cost isn't one flat number. It's this massive, sprawling range. And the difference between the best and the worst AI models is absolutely staggering.
The researchers who dug into this put it in a way that, well, it's a real jaw-dropper. They've found that the most energy-hungry AI models chew through over 65 times more energy than the most efficient ones for a similar task. A 65x difference. Let that sink in. That's not a small tweak. That's a chasm.
In this chart right here, this is what that 65x difference actually looks like. It's mapping out the energy used for a query across different AI models. Now, it's super important to notice the scale on the left. It's logarithmic. That means the differences are way bigger than they even appear. Up at the top, you have the energy hogs, and way, way down at the bottom, you have the super efficient ones. That huge gap is what we're talking about.
And no surprise, this huge variance isn't just about energy. The exact same crazy pattern holds true for water. This chart shows some models are just taking a tiny sip while others are absolutely guzzling it down. Those same energy-intensive models can consume over 200 milliliters of water for just one long query. That's almost half a plastic water bottle, just to get one answer from your computer. So here's where it gets really interesting. It turns out, it's not just the AI model that matters. It's where it's running. Just look at this. This is the exact same model, DeepSeek R1. When it's self-hosted in a less efficient setup, it's using over 29 watt-hours and 200 milliliters of water. But run that same exact model on Microsoft's super-efficient Azure cloud, and the cost just plummets, down to 7 watt-hours and only 34 milliliters. That's a drop of over 70%, which proves the building it's in can be even more important than the AI code itself. Okay, so we've been looking at the cost per query. Tiny little amounts. But these tiny costs are happening hundreds of millions of times every single day. So what happens when we zoom all the way out and calculate the true global cost of just one of these popular models?
For this, the researchers focused on a model many of us have probably used, GPT-4o. They ran the numbers to project its total environmental footprint for the year 2025, based on its insane growth. And the results? Well, they're honestly kind of hard to wrap your head around.
Let's start with water. The projected minimum amount of water that GPT-4o will consume in a year just from answering our questions is over 1.3 billion liters.
A billion liters. It's just a big, abstract number, right? So what does that actually mean? Well, it's enough fresh, clean drinking water to meet the annual needs of 1.2 million people. All of it consumed and evaporated by just one AI model in just 1 year.
And then, of course, you've got the carbon footprint from all that electricity. The projection for GPT-4o is a minimum of over 138,000 tons of CO2 equivalent emissions in 2025.
And to put that number in perspective, to absorb that much carbon from the atmosphere, you would need a forest roughly the size of the entire city of Chicago. A Chicago-sized forest just to offset the carbon from one model for 1 year.
So the solution seems obvious, right? We just need to make AI more efficient. Problem solved. Well, not so fast. This is where the whole story takes a final, really counterintuitive twist. It's a phenomenon called the efficiency paradox.
It's based on this idea from way back in the 19th century, believe it or not, called the Jevons paradox. It basically says that when technology makes using a resource more efficient and cheaper, we don't always end up using less of that resource. In fact, we often end up using way, way more.
So how does a dusty old economic theory apply to cutting-edge AI? Well, it's a perfect fit. Think about it. As AI gets more efficient, what happens? It gets cheaper and faster to run. And when it gets cheaper and faster, what do? We use it for everything. It gets baked into all sorts of new products. And here's the paradox. This explosion in total usage could cause the overall global consumption of water and energy for AI to just skyrocket, even while the cost of each individual prompt is getting smaller and smaller.
Which leaves us with this huge, critical question for the future of all this technology. As AI gets smarter and better and more efficient, can we actually stop it from getting hungrier and thirstier on a global scale? That, right there, is the billion-liter question.